Lecture 3.2, Thermal Systems. In this lecture, we'll look at two different types of systems in thermodynamic equilibrium. The first will be a system of particles. The second will be a system of electromagnetic radiation, or photons. So here's a simulation of a bunch of particles bouncing around in a box. When they interact with each other, they collide and exchange kinetic energy and momentum. As this system evolves, it settles into a state of thermodynamic equilibrium characterized by temperature T. You may remember that in these kinds of thermal systems, the mean kinetic energy of a particle is given by 3/2 kT, where K is the Boltzmann constant. And T is, again, expressed in kelvins. Here's a graph of the number of particles that are at a given speed in this kind of system. So you'll see that on the horizontal axis is the speed, and on the vertical axis is the numbers of particles at that speed. So very slow particles are over on the left-hand side, and we see that there aren't very many of them. If you look at the simulation, you might every once in a while catch a particle going super slow, but it's pretty rare. Also, sometimes you can catch some particles going super fast just by chance, but again, that's pretty rare. Usually what you see are speeds that are somewhat around the RMS velocity indicated by this second dashed line. So here's our graph again, and here is the formula describing this distribution function. So this little n is the number density of particles. So that's the number per unit volume in the sample. T is the kinetic temperature, and it shows up in this exponential term and also in this coefficient out in front. K again is the Boltzmann constant. So there are two common ways of characterizing a typical velocity of a particle in this distribution. The first is the most probable velocity, and what that means is the velocity that's associated with the peak of this distribution. So at the very top, draw a line down, that's the most probable velocity. So one can show, actually, by you simply take the derivative of this expression with respect to velocity, set that equal to 0, because that's where the top is defined, and you can solve that the most probable velocity is a square root of 2kt over m. If you rearrange this term, you can find that kt is equal to 1/2 mv squared. So in other words, the kinetic energy associated with the most probable velocity turns out to equal kT. And kT has units of energy, just like 1/2 mv squared has units of energy. So we'll come back to this in just a minute. The second way of characterizing a typical velocity in this distribution is the RMS velocity. So the RMS velocity is given by the second dashed line, which is shown in blue here. And it turns out it's equal to the square root of 3kt over m. This is the velocity that you get if you ask what is the average kinetic energy of particles bouncing around in the box. And it turns out that that mean kinetic energy equals 3/2 kT. This is a well-known result in thermodynamics. So there's a homework problem to actually verify this. So verify that the mean kinetic energy per particle is equal to 3/2 kT, and in order to do that, you actually need this the result of this integral over here. So to solve this problem, we need to look at the definition of this angle bracket notation. So if you want to take the average of a quantity, g of v, say, over the distribution function, that's equal to the integral of that function times the distribution function dv. So we integrate over all the velocities. So in our case, The thing that we want to take the mean of is the kinetic energy, so G is going to be 1/2 mv squared. And the distribution function is the Maxwell-Boltzmann distribution. So that's the thing that we had on the previous slide. In order to do this, we need to make a substitution. We look at the exponent here. So that exponent has an mv squared over 2kt. We're going to set that equal to x. Take the derivative of it, so you can get dx in terms of dv. When you make that substitution, this quantity turns out to be 1/2 m times the mean of v squared times a bunch of stuff here. These are a bunch of constants and things. And then the integral of x to the 3/2 e to the minus x dx. And that thing right there is what we were given as an integral that would be useful. So we'll just take that, plug that in once we get to that point. But so you would have to work out the details of this to try to figure out what this stuff is out in front to show that this is true. So this result that 3/2 kt equals the average kinetic energy per particle tells us that, when we talk about temperature in kelvins, we really are just talking about what the mean kinetic energy is of the particles, say in a gas or solid or whatever. So this term kt, again, has units of energy, and it's just really helpful to kind of have a order of magnitude idea of what kt is for different temperatures. So at room temperature, which is around 300 Kelvin, turns out that kt is pretty closely equal to 1/40. Again, that's just a ballpark number, but that's something to keep in the back of your mind. So a fraction of an electron volt. When you go up to temperatures, close to the temperature of the sun, you're talking about particles having a mean kinetic energy of about 1/2 an electron volt. And at the core of the sun, about 15 million degrees Kelvin, every particle has about over 1,000 electron volts of energy. In empty space that has a temperature of 3 Kelvin, we'll talk about that later in the class, every particle has very little energy, or less than 1,000th of an electron volt just out in space if it's in thermal equilibrium. So these correspondences are really useful to kind of keep in the back of your mind when we're working on problems in this chapter. In this second example, we'll look at the case of a radiation field that's in thermodynamic equilibrium with its environment. Usually when this result is derived, you imagine photons to be in an oven that's held at a fixed temperature T. But as it turns out, the result is equally applicable to objects that are in local thermodynamic equilibrium that are radiating outward into space. Blackbody radiation is the radiation field emitted by an object in thermodynamic equilibrium. The intensity of this field as a function of frequency is given by the Planck function. This is the equation, and then this shows the Planck function plotted as a function of frequency. The leading frequency to the third power causes the function to rise upward rapidly, and this 1 over the exponential term causes it to go back down at high frequencies. The plot is a visualization of the Planck function at a temperature of 6,000 degrees Kelvin. And the units of this thing are in watts per meter squared per steradian per hertz. And we'll talk a little bit more about the specific meaning of the units in a future lecture. For now, just think of it as the brightness that the object is radiating. While it's convenient to use frequency for describing this radiation field, for most of our purposes, we're going to be using wavelength, since that's what astronomers typically deal with. So it turns out you can transform that distribution function into one that depends on wavelength instead of frequency. If you make the substitution that wavelength times frequency is the speed of light, and then differentiate it to get a relationship between d nu and d lambda, you can plug those into the previous expression to get this new distribution function that depends on wavelength. And so it looks pretty similar here when you plot it, but notice that the x-axis is now in terms of wavelength in nanometers. So 500 nanometers is here, so the visible part of the spectrum goes from here about 400 over here to 700. Over here on the right, that's infrared, and over here is ultraviolet. It's more convenient to use nanometers instead of frequency. So the Planck function depends on temperature in two interesting ways. Plotted here are the Planck curves for three different temperatures, so 5,000 degrees Kelvin, 6,000 Kelvin, and 7,000 Kelvin. 6,000 is close to the temperature of the photosphere or the surface of the sun. So this is comparing the thermal radiation given off by the sun with a slightly hotter star and a slightly cooler star. So the first result is called Wien's law, and it says that the maximum brightness of the Planck function is inversely proportional to temperature. So the maximum brightness means just the peak of this distribution. So the wavelength where that peak occurs, so if we look at the peak of a 6,000 Kelvin emitter, bring it down, it looks like it's roughly around 500 nanometers. It's a little hard to tell, but if you go to a cooler object, 5,000 Kelvin, it's slightly at a longer wavelength, and this hotter object is at a slightly shorter wavelength. So as you increase the temperature of the black body, you shift the peak brightness to shorter wavelengths. The second result is called the Stefan-Boltzmann law, and it says that the total radiated flux is proportional to the temperature to the fourth power. So the total radiated flux means the power emitted in all directions at all wavelengths by the object. So it's basically the area under each of these curves. So if you integrated the total radiation across all wavelengths for a 5,000 Kelvin object and compared that to the total radiated by a 7,000 Kelvin object, you can see that the area under the 7,000 Kelvin object is much greater than the cooler object. So as you increase the temperature just slightly, you get a lot more energy out at all wavelengths. So here's an illustration from a textbook that is kind of nice. It superimposes the visible part of the spectrum, and it compares three different temperature stars. So there's a 3,000 Kelvin star, which is a fairly cool star, a 6,000 Kelvin star, which is similar to our sun, and a 12,000 Kelvin star, which is hotter than our sun. The point of this illustration is to show that the peak, according to Wien's law, the peak of the brightness shifts to shorter wavelengths as you heat up the object. So at 3,000 Kelvin, the peak is out here at around a micron in the near infrared. At 6,000, it's in the visible part of the spectrum, and at 12,000, it's shifted to the ultraviolet. So if you look at how the Planck function cuts across the visible part of the spectrum, you can see that a 12,000 Kelvin object is giving off way more violet and blue wavelengths than red light. So since you have so much more energy coming out at shorter wavelengths, the star is going to look kind of bluish. If you look at the red star, or if you look at the cooler 3,000 Kelvin star, the Planck function is still sloping upward across the visible part of the spectrum, so more light is coming out at the red end of the spectrum than the blue end, and cooler objects therefore will look kind of reddish. Stars like our sun are kind of in the middle, and so they are fairly neutral in color or white. So the takeaway from this is that hotter stars are bluish in color, cooler stars are reddish. Here's a little chart showing the relationship between the temperature of an object and where the maximum intensity of the radiation is from the thermal radiation coming out of the object. So that's the lambda max value. So a star that is several thousand degrees Kelvin, it'll be peaking in the visible part of the spectrum. As you heat up an object, so super hot stars might be close to 29,000 Kelvin. Most of their energy is now coming out in the ultraviolet. If you have a gas, let's say at the center of a star, you can be up in this range, so millions of degrees Kelvin, and the radiation associated with that gas would be in X-rays or gamma rays. If you go the other way, if you cool an object down, then the wavelength where that energy is radiated shifts to the near infrared, far infrared, and then microwaves. So let's look at a simple example. Let's calculate the peak wavelength of the sun spectrum, assuming the sun has a surface temperature of 5780 Kelvin. All right, so we'll just plug in the temperature of the sun into Wien's law, which says that the maximum wavelength is 0.002898 meters Kelvin. We divide it by the temperature of the sun in Kelvin to get 5.01 times 10 to the negative 7th meters. Convert that to nanometers, and that's 501 nanometers. So that's actually kind of a bluish green color. So you might wonder why the sun isn't green. If the peak wavelength is in the green part of the visible spectrum, why doesn't the sun look green? I'll leave that for you to contemplate. It's an interesting question that there's several different ways of thinking about it, but see if you can figure it out. All right, here's another example. Let's find the total power emitted by 1 square centimeter from the surface of the sun. We're going to use the Stefan-Boltzmann law for this. So the total power is equal to the flux times the area. The flux is given by the Stefan-Boltzmann law. Flux is sigma times T to the 4th. Plug in Stefan-Boltzmann constant, temperature of the sun, raise it to the 4th power. You get 6.33 times 10 to the 7th watts per square meter, which is kind of amazing. That's 63 million watts given off by every square meter of the sun. Of course, we want to know how much is emitted by 1 square centimeter, not 1 square meter, so the area is 10 to the negative 4th meters. Multiply that by the flux, and we get 6,330 watts coming out of every square centimeter. So you could imagine 63 100-watt light bulbs all shining out of something the size of about a penny. The sun's pretty bright. In fact, we can figure out just how bright it is. So this example asks us to find the luminosity of the sun given its radius and its surface temperature. The luminosity of a star or any object equals is the total power emitted by the object. So we use the same relationship we just had. We'll take the area that is radiating. It's just the surface area of the sun, surface area of a sphere. So since the surface area of a sphere is 4 pi r squared, we plug that in for the area, multiply that area by the flux, and we get this very useful expression that relates the luminosity of a star to its radius and temperature. All right, so we'll plug in, this is the radius of the sun that we got from up here. There's the temperature, Stefan-Boltzmann constant. And we find that the sun has a luminosity of 3.85 times 10 to the 26 watts, which is pretty close to the accepted value. So it looks like we did a pretty good job. Finally, let's compare the relative luminosity of a red 3000 Kelvin star with a white 6000 Kelvin star. We'll assume that the red star has a radius that's about twice as large as the white star. So this is kind of drawn to scale. So we want this red star to have twice the radius of this hotter, whiter star. So we'll define star A as the red star. So this is the expression for the luminosity that we had on the last slide. There's the temperature of the red star, and then we know that the radius of the red star is twice the radius of the hotter star. So here's the same expression in terms of the properties of the second star, of hotter star. There's the temperature, and what we're going to do is just take a ratio of these two equations. So divide the top one by the bottom one, you get LA over LB equals RA over AB squared times the temperature of star A over temperature of star B to the fourth power. The 4 pi's and the sigmas cancel out. So we know that the radius of the first star is twice the radius of the second one, so we get 2 over 1 squared. But the temperature of the first one is half the temperature of the second one. So it's going to be 3,000 over 4,000 to the fourth power. So we basically have 4 times 1/16, which will give us 1/4. So this means that the hotter, smaller star is 4 times brighter than the larger, cooler star. So even though this little star has only 1/4 of the surface area of this bigger star, because of its temperature, it's actually outshining it by a factor of 4. All right, here's a homework problem. Suppose we are given 2 stars, one red, one blue. Now we're going to assume that the stars have the same luminosity. So they're giving out the same total power. If the red star has a temperature of 3,000 Kelvin and the blue one has a temperature of 25,000 Kelvin, how much larger is this red star compared to the blue star? All right, so again, you'll use the exact same relationships we saw on the previous slide. So one final note, this is an interesting result that comes up in radio astronomy quite a bit. When you go to very small frequencies in the small frequency limit or the low frequency limit, so when h nu of the radiation is much less than kT, remember kT is a estimate of the energy of a thermal system. So when h nu is much less than kT, the Planck function is well approximated by the Rayleigh-Jeans limit. So the Rayleigh-Jeans limit is actually what you get when you try to derive the distribution function for radiation using purely classical techniques instead of quantum results. So anyway, this is what you get for the Planck function in the Rayleigh-Jeans limit, that the intensity is proportional to the frequency squared. So that is given by this blue curve. And you can see that these two diverge. If you go to large enough frequencies, these things diverge. The blue curve just goes up to infinity, whereas the actual function comes back down. But at very low frequencies, the two are actually in very good agreement. So we'll come back to this when we talk about applications in radio astronomy. This will be a handy result. Okay. In the next lecture, we will talk about the Bohr model of the atom and spectral lines.